Hello, good morning. Thank you for having us today. So my name is Francois Bobier. I'm a partner and vice president at BCG.X, our AI and data science unit. And I'm going to share with you a 6-month collaboration we did with BMW that results in a paper that you can find in archive already today, and a code that will be soon be made available in GitHub. And so let me just give you some of our project objectives. So we wanted first together to solve a real business problem, not a theoretical problem. We wanted something that is at the edge of quantum computing science. That's why we chose DQI. I'll go to that a little bit later on. We wanted that research to be shared publicly. So what we have built, and Carlos will talk about it, can be improved, and we hope that people will work after us and improve some of the code we couldn't improve and make that innovation available faster to everybody. And also, we wanted not to cheat. So meaning that we were hoping we would be able to demonstrate quantum advantage or not. We needed to benchmark our technique with the best classical techniques. And the good thing about BMW is that they have people who are very used to use the best classical algorithm optimization. And in that case, we use Bobier. And we benchmark ourselves against the best classical method available. So for us, that was what we wanted to achieve. So why BCG is so interested in quantum? Because we believe it's going to generate an important value over time, probably something like $600 billion for users, and sustain a market about $100 billion for end users. For the quantum computing market. So that's going to be an important part of computation, similar to HPC in a way. And when we did this market assessment, we looked at 4 different use cases. So a lot of them are very famous, but we are gonna double click on optimization, because that's the problem we chose with BMW. Why quantum has an advantage in optimization is that quantum can explore a vast space in a single computation, as opposed to classical solvers. They have a function f, and they need to do f of x multiple times to find the right solution. Quantum is able to explore, thanks to superposition, a much wider space, and to find global solution instead of local solutions. Until recently, the best quantum methods were all using a principle of nature, which is energy minimization, right? Energy is the basis of everything in nature. Even the color of my shirt today, you can only use quantum mechanics to know the color of my shirt if you know the molecule, because the color is the wavelength, right, of the energy that is between the excited state of the molecule and the ground state. You divide that energy by Planck constant, and you get the wavelength of my shirt, and there's no other way you can know it, right? Nature is very good with finding minimum of energies, because this is what nature does every day, right? Instantaneously, right? And so most of the techniques we have been seeing so far in quantum involve using that capacity for nature to find a minimum of energy, or also using tunneling to jump and go to a better solution in the same function. But they all use those intrinsic properties of nature. And last year, Google came up with a new algorithm called DQI. They proposed it last year. By the way, it's still not published. It's still on archive. So you will probably find a publication very soon in a major publication about it. And Google came up with a complete different approach that does not use energy minimization, but basically you create a quantum state that generates interferences patterns, and you find the solution at the interference. And that's a complete different approach. What is interesting about DQI is that it gives you it's a completely new technique. And so it can give a real advantage, and we'll explain to you what we have shown. Why I'm still on that slide, it's important to note that there was a reason also why the first technique was used until now, because the first technique is still amenable to NISQ machines that we have today, right? The noisy computers that we have today, they can explore space like that, they can do the tunneling, and there are practical techniques that fit within the current NISQ machine that use these adiabatic techniques. The problem with DQI, when we started to do it with Carlos and the team, is that we knew we need a logical computer to do it. We need logical qubits to do it, because you read the exact solution at the interference patterns. You read a sequence of 0 and 1s that gives you the answer to your problem. And you cannot flip 0 and 1. If I speak in decimal terms, there's a big difference between 100 and 10. Yeah, decimal has moved, but the answer is completely wrong, right? So for DQI, the prerequisite is that you need an error-corrected machine. So when we embarked on that journey, we knew that we couldn't run it on current hardware. However, we knew that we could run it on simulators, with up to 40 qubits, because this is what we can simulate with, with error correction, so to speak. So now let me speak about the problem that we chose, and it's very specific to the car industry. I don't know if you are aware, but the cars are the most complicated product you can ever imagine. There are thousands of parts in a car. And I'm just talking about physical parts. There are also different software parts. They need all to communicate to one another. When you buy a car, you select a lot of things as a customer. You select the color, you select the engine, you select maybe the connected services that you're going to have. You select whether you're going to have a sunroof or not. You select the type of trims you want, the type of tires, and so on and so forth. So even in the mass market, I used to work, for example, for Renault. Inside Renault, a car is a vector of about 250 parameters, right, to describe the car. You can imagine in luxury companies like BMW, you got a lot more parameters because it's luxury, so you can also personalize the interior, and there are many different options. And a funny statistic, but you can make billions of cars that could be manufactured in a factory and would look very nice on the road. That's one statistic for you. And another is that in a typical month in a BMW factory, they never make twice the exact same car, right? So just think about that. So the problem we were trying to solve is that, of course, you could go to the customer and say, look, you have a blank car, drag and drop the engine, the trim, the sunroof you want, and basically you will pay the car based on your selection. First of all, it's not very practical. You can go to BMW configurator, you will see there's a lot of different options. And second, you end up with a very high price because options, they tend to be expensive. So marketing has to make a choice between what are the base packages, right, that they are offered to the customer at a certain price, typically discounted compared to the cost of the individual options that go inside that car, and the additional option or top-ups you can choose once you have selected that base package. Remember the number of parameters you have to optimize. It's actually a very difficult problem. So we were able to translate it into a mathematical problem with the BMW team. And from there, we could start to apply DQI, and I'm going to hand over to Carlos to explain how we did that.
Thank you, Jean-Francois. So, good morning, or good afternoon. So I'm Carlos. I'm part of the quantum team at BMW and part of this collaboration with BCG. So as Jean-Francois said, like the first thing we did was try to understand how to model this problem mathematically, right? And maybe, okay. So once we have the model, at the end of the day, what we have is an optimization problem, and we write it in a particular mathematical way, and we have all the parameters, and these problems are enormously complicated. So because we are in the quantum team, we want to understand how new algorithms, I mean, what's the amount of work that you need for these things to work. So first of all, this is a problem itself, getting the mathematical problem, right? And as Jean-Francois mentioned, we have benchmark related to the best classical algorithms. So once you have the problem in this form, then you take Bobier and you just put it there, and then you just wait a bit, and then you get the solution. And as Jean-Francois mentioned before, we saw that about a year ago there's a DQI paper from the Google team. We're like, okay, that sounds interesting. And the reason we found it interesting is because they have one particular problem instance in which they actually show quantum advantage of exponential separation between the best classical algorithm and the DQI. So we thought, okay, let's see what happens when you take a real problem and then they try to do all the stages of the problem. So now we have here in this slide, so the DQI uses interference in order to get, prepares a state, you do the structure of the problem via the quantum Fourier transform, and what it basically does is it piles the probability of measuring the optimal state, so it makes it bigger than random. So the first thing you have to do after you do the problem definition, you have to transform the problem to a different type of optimization problem. In this case, this is called a max XOR SAT. So it's a type of satisfiability problem in which you want to maximize as many constraints, as many logical constraints. In this case, in mod 2, like for the technical people in the room. So you write it this way. So this B is a matrix, and this matrix basically encodes the optimization problem. So what we've done is take optimization problem, transform it to a different type of optimization problem, max XOR SAT. And then the super interesting thing that DQI does is it interprets that optimization problem into a decoding problem of classical error correction code. So this B is like a parity check matrix, and a crucial part of the whole process, right? So you have your quantum system, you need to encode B and this is small vector V, and then you have to do this decoding step. And this decoding step basically like the interpretation of the optimization problem as an error correcting code. And the power of the algorithms, if you can decode, quote unquote, as many errors as possible, so you have a good code and a good decoder, then you will have a good solution of your problem. So you do this, and then you make your measurement, and hopefully you have your solution of problem with high probability. So our contributions, understanding what the problem is, providing a form of doing this transformation, and providing a quantum implementation, like bottom-up type of implementation. So I don't think we will go into all the details, but this is a zoom in of the top part. So everything that is required for this to work, right? So there is like a DQ state preparation. We need to encode the phases of the quantum system. Then we need to encode the syndrome in this language of error correcting code, basically with this matrix B. Then we need to provide a circuit in which we use a version of these belief propagation algorithms, like we implemented as a quantum circuit in a coherent way. To do part of the calculation, we need to repeat this several times. So we provide these blocks of code that does this part. Then we have to take basically the Fourier transform of the system, and then you do the measurement. As Jean-Francois said, we have all the steps explained, in a paper, like basically doing everything that you will really need to do, which is, the objective. We need to understand how these things work. So let's show you the results. So the results are not super great, let's say. So here in the x-axis, we have the problem size. The way we did it is number of variables times the number of constraints that you need to satisfy. And then here is the fraction of the number of constraints. So more like higher fraction, it's a better result. So baseline, so we do random. These problems are tiny problems with respect to what you can have. I mean, these numbers can go, exorbitantly large. So baseline, this is what you do if you just randomly sample for a solution. Then if you do Gurobi, then you get like about 85%. And then, with the capability that we have to simulate, this is very important. We can only simulate the correction of 2-3 errors. We would like to have, if you have a quantum computer, you could ask the decoder to decode for larger amounts of errors, but we can simulate. So we have, I would say, a very modest. See, it's better than random, but it is not, by a long shot, better than the best result that you can have with Gurobi. But the expectation, we saw during this conference all these plots, right? The one grows like this, and the other one quantum, and then there's still room for that, because we will be super far here where we are able to see the quality of result of Gurobi going down. So there's still space for improvement. Then the other thing we did was we look at the resources. I mean, you use our implementation in Qiskit, and then we just count the number of qubits. Then you see that here we can do a little bit bigger problems because we don't have to simulate, we're just counting. So we have bigger problems in the number of qubits. Then you see that the scaling is not exponential, which is good. And then the number of gates that we've used, we put the code, we run the transpiler of Qiskit, and then we just say this is the number of gates. And then here, each of the different colors is for the number of iterations that we do from our quantum decoder, so the number of times we use our decoding circuit, which is also good. That is not exponential. So just to give you an idea for a problem that, these problems that I show you, they're very, very small, so they're not industrialized. That's why it's towards solving these problems. So now for like a problem that is a bit more real, then we'll need, thousands of qubits and hundreds of thousands to millions of gates, which are very, very far away from what we can, do with hardware today. So I think we're getting to the end of the talk. So there are a couple of things that we have learned across. Oops, how do you go back? Yeah. So there are a couple of things that we learned, along these 3 dimensions. In terms of quality, I mean, we know why there is this gap. There are a couple of things. The mapping that we've done from the optimization problem to the satisfiability problem, I think, can be improved. And I mean, we have a couple of ideas to improve that, and also the quality of the decoding algorithms that we found a quantum implementation can also be improved. So these are possibilities for continuation of the project. Then, in terms of performance, we see that the scaling of quantum resources is better than what we expect from classical resources for as we go very, very big problems. But again, the ones that we can actually show, they're very, very small. The ones that we actually can compute, and like we could go farther if we crash basically the Qiskit transpilers, trying to make the problem bigger and bigger, just to see if we can see some sort of crossover between the DQI result and the Gurobi and so on. And also, the problem, the nature of the problem, that there is a significant overhead between, like during this transformation to this max XOR SAT problem, that maybe, if one can have problems already in that form, maybe this is a better use case for this algorithm. And with this, I think we can conclude. Thank you very much.
Thank you.
We have a couple of questions from the audience for you guys. Okay, so first, how many error-corrected qubits have you used for your simulations?
Error correcting? None.
We use simulators on classical hardware, and I think we had 30 each.
I mean, you know, like in terms of qubits, like for simulation, we've done 26, but they are like, you know, ideal. There are no error correction. There is nothing on top of that. It's 26 for, I think, the biggest one that we showed.
Okay, and how does the number of decoders scale with the problem size?
Again, the number of?
The number of decoders. So this is referring to the slide with the you showed with the two plots.
So like maybe the question would be the number of errors that you can decode. So if you have a good low density parity check code, I think they should scale like the number of errors should scale linearly with the number of I think with the number of variables. But in our case, that was not the case because our mapping was probably less ideal. So that the scaling, I mean, I cannot give you the numbers. Maybe if anybody wants to talk the details offline, maybe we can, you know, go over the paper and so on. Things will get clear.
Okay, and finally, one more. In classical error correction codes, there's a limit of error correction. When used for optimization, is there also a limit of minimization capabilities?
Yeah. I mean, I really do not know how this compares, but at least in the original paper, what they did is they built some low-density parity check codes that were almost at the limit, you know, about, I think the error rate was, don't quote me exactly on this, about 13%. And we are very, very, very far away from that.
Okay. Thank you very much. Let's thank our speakers again.
Thank you.